Okay, welcome back. So, if you didn't watch the video from yesterday yet, go to the description. I'll actually put the link over there. So watch that first and make sure you understand the idea of how we're going to solve this problem before coming back and move on and watch the actual proof of it. Okay, so we're going to continue and do the actual proof. In yesterday's video, we showed that we could try to make regular polygon inside of the circle, so that we will try to do a comparison. And again, that's what we call it analyzing. We're doing analysis to prove the inequality above. But we start with the polygon with the least side that we know of course, in high school geometry, which is triangle. And unfortunately, it doesn't work. So what can we do? Let's try to double the amount of side of the polygon, so that we will see if we can actually get something else. So what should we try? A hexagon with 6 sides? Well, this is what we usually would do. Double it first and then see if it works. Unfortunately, that would not work either. So let's double it again. We're going to take the decagon, meaning that we have a 12-side regular polygon. Okay, so what do? We're going to divide up this regular polygon evenly, like how we cut a pizza, like this shape right here. So we're going to draw a line from the center of the circle, which is also the center of the regular polygon in this case, because this is this polygon is actually having the the circle is called the circumcircle of the polygon, where all the all the vertices of the polygon are actually aligned on the circle. Good. So if we try to draw the center to any of the vertices, of course the length will be the same, because all the vertices are actually on the circle. So the radius, the length will just be the radius, r. And more importantly, we have a regular polygon, meaning that if we draw the lines from the center to the edge to get the radius right here, here, and so on and so forth, we actually will divide up this polygon evenly and get exactly that many pieces of triangles. So if we have an octagon, meaning that if we have a regular polygon with 8 sides, then we'll develop into 8 congruent triangles. And here we have a dodecagon, meaning that we have a 12-sided polygon. We're going to divide up into 12 congruent triangles, like this. And I'm not going to draw all of them, because again, since this is a regular polygon, the length of each edge is the same. So now we just need to figure out the edge of one of the edges, and then multiply by 12 to get the total length, known as the perimeter of the regular polygon. So we now just need to focus on one of the triangles, and I'm going to draw that triangle down here so that it's easier to understand. So keep in mind, the bottom line right here is actually the edge of the regular polygon that we started off with. Now, we also know that these 2 sides are actually the radii of the circle. Each one is a radius. Good. Now the question is, how do we tell the angle of this triangle? And when I say the angle, I'm talking about the angle between the 2 radii. Well, keep in mind, we just said that we divide up this polygon into exactly 12 pieces that each triangle is the same as another. So if we know that a cycle is 360 degrees, and we are now dividing up 360 degrees into 12 equal pieces or angles, then each angle will just be 1/12 of the whole cycle, 360 degrees, meaning that, let's call it angle alpha. So it means that each angle that is pointing at the center right here is 30 degrees. Good. Why? Here is the reason. Since we have 30 degrees up here, we also know that on the bottom, we will have 75 degrees each. Again, we can just draw a line from the center, which is on top, to the bottom and make the altitude. Okay, meaning that we have a right angle here. And we also will divide up this triangle with two sides the same, also known as the isosceles triangle, into two congruent right triangles. And again, you can just prove it. Well, you probably have seen the proof in the geometry class, or if not, you can just try to prove it with some basic geometry. But in this case, if we divide up into two congruent triangles, the angles up here will also be divided up evenly. So it'll be 15, not 75, 15 degrees each. Good. And since we have a right triangle, the remaining angle will just be 90 minus whatever we have, 15. So we get 75. Now, we know that for right triangles, we only have 30, 60, 90, and 45, 45, 90 that are taught in school. But this is also one of the special right triangle that I suggest everyone should know of. And again, there are two ways to do it, but you can also try to memorize it. And again, my first video in this channel is exactly talking about how to find out the ratio of a right triangle of 15, 75, 90 degrees. So in this case, if we have the radius be our hypotenuse, then we have a special ratio that the bottom line here, the longer leg, will be radical 6 plus radical 2 over 4 times the radius. Okay, and then for the shorter leg, we will have radical 6 minus radical 2 over 4 times the radius. Good. So what does that mean? It means that this purple line here, which is known as the edge of the regular polygon, we know that is divided into two even halves. So the length of the purple line will be 2 times of this value here, times 2. So we get radical 6 minus radical 2 over 4 times 2, which is over 2. Good. And now we just need to finish up our proof now. So from the definition, we say that pi is the ratio of the circumference over the diameter, or known as 2 times of the radius. So this gives us pi is equal to, of course, not necessary to do it this way, but it'll be better if you just copy it so that you know where to start off. Then again, we just said that from the figure, the circumference of the circle must be greater than the perimeter of the regular polygon we draw, because the regular polygon lies inside of the circle that we have. So in this case, the perimeter will be smaller than the circumference, or the circumference is greater than the perimeter. And we're going to divide both sides by 2r again. Why? Because r is the radius, is positive. So if we divide by a positive value, we don't need to change the inequality sign. Good. So we can now split into this. 1/2r times the perimeter. Now we need to figure out the perimeter of this regular polygon. Again, this is a dodecagon, meaning that it has 12 sides, and we say that it's a regular polygon, so that the perimeter is just the number of the edges, which is 12, times the length of each edge, which is the purple line down here. So we just need to do the substitution. It's 12 times the the length of each edge. Excuse me, like this. And then don't forget, there's an r here because we're multiplying by the radius. Multiplying by the radius, which is the length of the hypotenuse. Okay, so keep in mind this r is very important because now we can cancel it. Without the r, we will actually have a problem here because we should expect that the value that we're finding, pi, is a ratio. It should not depend on r, the radius. So now we see that r cancels out. Then we can just cancel out the 2 with 12. So this reduced down to 6. And then we can cancel out one more time. So we get 3, 1. Good. So we end up with 3 times radical 6 minus radical 2. Okay, so we're almost done to a proof, but I need to erase the board so that we will have a little bit more space to do the actual boring calculation. Okay, so from the last board, we end up with the following statement. Pi is already greater than the product of 3 times the quantity, radical 6 minus radical 2. Okay, so how do we finish our proof? Now we need to use the facts that we have. So since we want to show that this is greater than, then we also want to show that it's greater than the lower bound of this, lower bound of this number, so that if the lower bound is still bigger than this value, then this whole thing will be bigger than the lower bound, which is also greater than this. So this is what we are looking for. Now, we also have the minus radical 2. This time, we need to take the upper bound. Okay, so we now need to think carefully. Why do we want to take the upper bound of this part? Because we're trying to subtract it from this, meaning that here we're going to take the fact and then trying to see how we can manipulate it with it. So if we have radical 2 is between these two values, if we multiply both sides, all parts by -1, we end up with the following. So here is a scratch work. Now again, since we're multiplying everything by negative value, we also need to flip the sign, flip the inequality sign. So if we rearrange it, we see that we have the following. It is less than this, which is less than negative 1.4142. Good. So now, after we multiply by -1 and rearrange the order, we get the inequality up here to see that what is the lower bound that we will get with the negative sign. So that now we're going to do this. We will take these two and then add together. Now, if we do addition or subtraction of inequalities, no matter if it's positive or negative, or just, plus or minus, we don't have to flip the sign. So now we're just adding everything together. So we'll take the left term and add the left term, the middle adding the middle, the right adding the right. So the middle we end up with radical 6 minus radical 2. Good. Now for the right hand side, which gives us the maximum upper bound, we have 2.4495 minus 1.4142. And when we do this, when we do addition, we are actually making our error a little bit bigger, but not too far off, okay? But this is still enough because all we care is we want to see what is the lower bound bringing us to. If the lower bound is still bigger than what we want, everything is fine. So what does that mean? Now we're going to do the subtraction here. So it means that we can now know that this value cannot be bigger than this number, okay, by approximation. And we actually, if we be more accurate, we will know that this number is actually a little bit smaller than here. We'll end up with a 2 here and then something else there, so that we actually get even more strict condition. But this is actually enough for us to prove this. So we're now going to take the lower bound part. So we end up with 4 and 3 here, so that we end up with a 2. So we actually get the lower bound is this, meaning that we can guarantee that radical 6 minus radical 2 must be something bigger than this number. Okay, what does that mean? So it means that our proof is almost done. Pi is greater than this, which is strictly greater than 3 times the lower bound of it, because now we just use the fact that the part inside of the parentheses is strictly greater than the lower bound. 1.0352. So this is going to give us, let's see, we'll get 3.1056. So in fact, we actually get something even bigger. Well, to end the proof, we'll just write down that this number is greater than what we want to prove. Alright, I hope you all enjoyed this video. So don't forget to like and also subscribe to my channel so that you know more of my other videos. Turn on the notification so that you won't miss my new videos either. And if you think this concept is cool and perhaps you have never seen before, you can leave your comment below and also try to share it to your friends so that you can try to surprise them or let them learn something something new. Okay. All right, I'll see you guys next time.